Welcome to The Explainer. Today, we're diving deep into the proving ground for EV batteries. This isn't just about theory, it's a brutal gauntlet where promises are put to the test and only the toughest, most robust technologies actually survive.
So here's how we're going to break it down. First, we'll look at the fundamental challenge of storing all that energy. Then we'll put the reigning champ, lithium-ion, head-to-head with the challenger, solid state. After that, we get into the really good stuff, the exhaustive performance runs, the safety tests, and yeah, we'll get destructive, and finally, the deep chemical analysis that really separates the hype from what's ready for the highway.
All right, so before we can really appreciate the incredible complexity of a modern battery pack, we're talking systems running at up to 800 volts. We have to go back. We need to understand the basic principles that started it all, and the core problem that engineers are still trying to crack today. Okay, what you're looking at here is a Daniell cell from way back in the 1830s. Super simple principle, right? A chemical reaction kicks off, releases some electrons, and you get a current. But powering a 2-ton vehicle that has to go from 0 to 60 in a few seconds and then drive for hundreds of miles, well, that requires a system that is just on a completely different planet of power, reliability, and complexity. And this brings us right to the heart of the engineering challenge. You see, it's not about just making one thing better. It's a constant juggling act. You could design a battery with incredible energy density, but maybe it's totally unsafe. Or you could have a super safe battery that takes a whole day to charge. The real holy grail is finding that perfect, delicate balance between all of it. The energy, the power, the lifespan, and of course, safety.
Now, let's meet the two main players in this fight for dominance. In one corner, you've got the established champion of the world, the lithium-ion cell. And in the other corner, the revolutionary challenger that promises to change, well, pretty much everything, the solid-state battery.
So the really fascinating thing to see here is the huge architectural shift. In a typical lithium-ion cell, you have a liquid organic electrolyte, kind of like a chemical soup, and a porous separator that keeps the two sides from touching. A solid-state battery just throws that whole concept out. It replaces that flammable liquid with a solid material, like a thin piece of ceramic or a polymer that does double duty as both the electrolyte and the separator. And doing that, well, that's what lets you use a pure lithium metal anode, which is the key to unlocking massive gains in energy density. And these are the promises that come with that new architecture. Because you get rid of the bulky graphite in the anode and use that super efficient solid electrolyte, solid-state batteries are targeting energy densities of 800, maybe even 1,000 watt-hours per liter. That is a huge jump from today's best cells, and that translates directly into more range. And maybe even more important, getting rid of that flammable liquid electrolyte makes the whole thing a heck of a lot safer. Look, making promises in a press release is the easy part, but in the world of battery engineering, proving those promises means you have to subject these cells to an absolute gauntlet of intense, meticulous, and, yeah, often destructive tests. It's all designed to push them way, way past their breaking point.
This is where we separate the cool lab experiments from technology that's actually ready for production. And it all starts with the most fundamental question you can ask about any battery: how long is this thing going to last?
Cycle life is really the bedrock of all battery validation. It's not just about how many times you can charge and discharge it, it's about how much energy it can still hold after doing that hundreds or even thousands of times. This single number directly translates to the long-term value and usability of an EV.
And that specific threshold the industry uses is almost always 80%. The second a battery can't hold 80% of its original, brand new charge, it's pretty much considered to be at the end of its useful first life for a car. So if you see a cell that can hit, say, 1,000 cycles and still have 95% of its capacity, that's a massive achievement.
And this is where you can see the extra complexity that comes with solid-state batteries. For a normal lithium-ion cell, you basically just cycle it at different speeds, those are called C rates, and at different temperatures. But for a solid-state battery, that interface between the solid electrode and the solid electrolyte is super sensitive to mechanical pressure. You have to test it under a precisely controlled pressure, sometimes up to 200 megapascals, just to keep everything in good contact, and to physically stop these things called lithium dendrites, tiny, sharp needles of lithium that can grow and cause a short circuit. Okay, so endurance and performance are crucial, but we're talking about a device that stores an incredible amount of energy and carries people around. That means safety is, without a doubt, the #1 priority, and that brings us to abuse testing. This is the catastrophic failure that all battery safety engineering is designed to prevent. It's a vicious, self-sustaining chain reaction. A little bit of heat from an internal short causes a chemical reaction that makes more heat, which makes the reaction go faster, which makes even more heat. Then it all snowballs into this uncontrollable, super fast rise in temperature and pressure that can vent flammable gas and cause a fire. So to make sure that never happens, engineers have to intentionally try to make it happen in the lab. They will overcharge a cell, they'll short-circuit it, they'll crush it, and they'll literally bake it in an oven at over 130 degrees Celsius. The nail penetration test is probably the most brutal. They just drive a nail right through it. It's meant to simulate what might happen if a tiny metal particle from the factory got in the wrong place. The goal isn't just to see if it fails, but how it fails.
And this really shows how the safety challenges change as the technology does. So while solid-state batteries get rid of the fire risk from that liquid, they can introduce totally new chemical hazards. For instance, some of the most promising solid electrolytes are sulfide-based. And if they're exposed to moisture in the air, they can release highly toxic hydrogen sulfide gas. This means all of the testing and manufacturing has to happen inside a totally controlled inert atmosphere, like an argon-filled glove box.
So passing the performance and safety tests is the goal, right? But to actually improve the technology, to make the next generation better, engineers have to understand exactly what's happening inside the cell. We're talking at the chemical and structural level. This is where deep materials science comes in.
I mean, what is it that actually causes a battery to die over time? Is the cathode material physically breaking down? Are there side reactions happening with the electrolyte? Is the anode cracking? Answering these questions through some really deep analysis is the only way to design longer-lasting, more efficient, and safer batteries for the future.
This technique, XPS, is absolutely essential for understanding one of the most critical parts of the battery, something called the Solid Electrolyte Interface, or SEI. This is an incredibly thin layer, we're talking just nanometers thick, that forms on the anode during the very first charge cycles. XPS lets scientists see the exact chemical makeup of this layer, and that's so important because a good, stable SEI is what really controls the battery's long-term performance and its lifespan.
Now, to go along with that chemical analysis, engineers also need to see the physical structure. That's where a scanning electron microscope, or SEM, comes in. This lets them basically take a picture of the battery's guts after it's been cycled to death. They can spot tiny cracks in the electrodes, look for uneven clumps of lithium that might turn into those dangerous dendrites, and just generally check if the materials are holding up the way they were designed to.
Think of EIS as a really detailed electrical health checkup for the battery. It doesn't just give you one number for resistance. It can actually tell the difference between different types of resistance, like the resistance of the materials themselves, the resistance at the surface of the electrodes, and the resistance that comes from ions trying to move around. By tracking how all those little pieces change over thousands of cycles, engineers can pinpoint exactly where and why the battery is starting to lose its punch.
So ultimately, all of this super deep analysis has a very clear goal. It lets engineers benchmark a new cell design against the ones they already know and trust. It gives them the fundamental knowledge they need to slow down how the battery ages. And when a cell does fail, it lets them do a root cause analysis right down to the atomic level. All of that data then feeds right back into making the manufacturing process better, where things like automated X-ray and CT scans are used right on the assembly line to spot tiny defects, ensuring every battery that comes off the line is safe and high quality.
You know, the technology promises a complete revolution in range and safety, but as we've seen, the road from the lab to your car is paved with this incredibly demanding gauntlet of performance, abuse, and atomic-level testing. The challenge isn't just inventing a better battery anymore. It's proving it's better, proving it's safer, and proving you can actually make it cycle after grueling cycle. Thanks for joining this explainer.